record. Tamir, please.
Okay, hi, good morning, everybody. So today the topic is evaporation, but it's a little broader, and the idea is to kind of review limitation gaps of liquid and vapor water flow. And this will be kind of general, but also very specific to the limitation that limit us understand, model, evaporation. And this work is done with closely with Shmuel Asulin. So you see a lot of data coming from Shmuel to support the modeling. So first of all, kind of a general scope on what we're talking about. So here I show the global potential evapotranspiration. Basically, the global climate driver for water evaporation. And if we go from the north or the south to the center, we see that as we go to the center, the potential evaporation is higher. But when we go to the actual evaporation, and here we have a nice illustration of a monthly global actual evaporation, we can see that as we go to the center, and as we go to the south and north, we see that the actual evaporation is lower. So we are going to talk about today about actual evaporation. We want to understand the mechanisms of basically soil that limit evaporation and talk about how we model this. So global water cycle and water exchange between the soil and atmosphere. It involves mass and energy transport, phase exchange between liquid and vapor, and liquid flow and vapor diffusion within the soil. We will see that it is controlled by ambient conditions, which are the atmosphere, and by the transfer properties of hydraulic properties of soil or porous medium. Okay, so our motivation is basically centered about semi-arid and arid regions because in these regions, we barely have plants and there's a lot of exposed soil that we're interested to know how much of the precipitation that goes down on these soils or how much of shallow groundwater or groundwater can evaporate and quantify these. These areas are expanding from desertifications and higher temperature can make these evaporate. There's poor understanding and lack of quantitative tools for modeling and predictions. So what we want to do, and we will want to concentrate in this lecture, is a better understanding of the controlling mechanism, quantification of this process using characteristic features of the mechanisms and the soil properties. And this will enable us to construct a physically based modeling framework that will enable simulations and predictions for soil evaporation. And we want to keep it simple so it can be applied for larger scale. And what we're going to see in terms of the work today is, and the modeling is only macroscopic equations. So we're not going to deal with the microscopic mechanisms, but look at the volume average macroscopic equations. So these can be used later for larger scales, not today. I'm not going to show large scale modeling today. Okay, so let's talk a little bit about evaporation and hydraulic continuity. So, and this is important because this is basically how we think of the water distribution in the soil and later how we model it. So we can have two existing scenarios as we think. One is that there is liquid continuity, hydraulic continuity from the subsurface to the surface, and this is the left illustration. And in this feature, we have significant water liquid flowing from the subsurface to the surface with the atmospheric driver. Now, the second scenario is on the right, where we see that there is not much or drier area and a disconnection of liquid water and vapor transport from the subsurface to the surface. And this area, we denote it as the evaporative front, okay? So liquid can flow from the subsurface, deep subsurface, to an evaporating front, evaporate at this front, and diffuse upward to the surface. Now this basically liquid continuity defines the stages of the evaporation. So stage one is usually when we start from a saturated or nearly saturated column, is where the atmospheric condition drive this stage. And it's, as you see, and this is an example, but many experiments show this, the rate of evaporation is fairly steady. But once the soil cannot sustain this, evaporation's rates start to drop and reach this part where we have a diffusive layer that defines the evaporation rate. And this process, of course, is complex. And here we see work of Ben-Yerian et al., which studied these and under different temperatures. So the temperature is not only affects basically the evaporative demand, but also the water retention in the soil and the hydraulic conductivity. So we see a complex effect of temperature on this process. Okay, so the outline of today's talk, we just talked about the motivation, we talked about the evaporation stages. I'm going to start with Gardner's concept, which is still a leading concept today, and talk about limitations that we think this concept has, and then from these limitations, I'm going to show the proposed model and show some validation with experimental work, and then kind of look at open questions that I think are important for me to address in future work. Okay, so Gardner's approach, which I think led to it was a very important work at the time, but it led to a large misconception of the evaporation process. What Gardner says is, hey, look, if I have a water table, then I have some distribution of the water content until the surface. And from the surface, I have an evaporation. And this is the evaporation process. So if I look in the soil profile, I should find water contents in between residual and saturated contents. And of course, this assumes hydraulic continuity to the surface. But not only it assumes hydraulic continuity to the surface, another important feature is that there is the upper limit of the atmosphere is shown here as infinity. So when Gardner thinks about, or when you think about this problem as a liquid phase only problem, putting infinity here is not an issue, because of course the retention curve or the hydraulic conductivity with the liquid is defined from saturated 0 here to infinity to residual water content at infinity. But when you think about it, the real problem, we go to drier conditions, we go to the atmosphere, and we can evaporate those residual water content. So residual water content, we can think of it as, define it differently, but essentially residual water content is the water content that below it we don't have water flow. So if we look at the Richards equation, we have as h goes to infinity, theta goes to theta r, but in our problem, we should look at theta that goes to 0. And we can correlate atmospheric conditions to a much lower hydraulic head or a pressure, metric potential by the Kelvin equation. So these kind of pose the two major issues that Gardner or the model of Gardner is leading and still used today is 1, hydraulic continuity till the surface, and 2, what metric potential or what potential head defines this, even if we don't have hydraulic continuity, what defines this upper limit. Okay, so this is just to point out the limitation, and of course, I'm not the first one to look at this, and lower water contents with notable works of Tuller and Orr, who looked at film flow. So you can define a lower hydraulic conductivity with very high pressure gradients or pressures. And so this was work from Tuller and Orr, and this is work from the group of Derner. But the question is, what if there's no hydraulic continuity? Okay, so this can be used even to extend the hydraulic conductivity with a vapor flow. So basically we can get a continuous hydraulic continuity function, including liquid flow and vapor flow. And this essentially can solve our problem of modeling water flow continuously from a saturated water content to a 0 water content. Well, that would be nice, but all these functions rely on equilibrium. And now I want to talk a little bit about dynamic non-equilibrium and why that gives us a problem with when we deal with evaporation. So let's look at some imaging from these 4 images were taken at slow drainage until image D, okay, at about half a meter, whereas image E was saturated fast to the same half a meter suction. And you see that this image or this porous media is well drained, but this porous media, which was exposed to the same suction, was not drained. And that is because the fast drainage caused the disconnect, and the soil was not able to drain. And so these experiments were also done on larger pores, and you can see the same imaging. So fast drainage, slow drainage. The fast drainage cannot drain as much as the slow drainage. And you can see some 3D images of that. Also in a review paper, they looked at some non-equilibrium during evaporation. And what they saw is that, well, they measured the pressure head of 2 soils at the same depth during evaporation. And you can see this is the curve of the evaporation. And here they tried to connect the water content and the pressure head. So what they saw is that during evaporation, you have these jumps. And so you would have multiple pressure heads for same water content. And so this, and then they correlated that to these jumps and related that to hydraulic non-equilibrium. So this is during evaporation. So you would have a disconnect of hydraulic continuity depending on the flow rate or the evaporation rate. So this is to add our complexity. So with changing transition from liquid to vapor flow, we need multiple hydraulic conductivity functions that characterize this flow. Okay, so we cannot use a one single location of liquid discontinuity, say theta R, which then we go to a vapor flow hydraulic conductivity function and have a continuous, because liquid continuity is disrupted at different thetas or different H depending on the flow rate. So it's problematic to characterize such flow with a continuous hydraulic conductivity function. And therefore it's beneficial to use a vapor only zone with diffusion and not with hydraulic conductivity beyond that point. And this is where we come to the proposed model. If we want to basically delineate this process, we can separate the evaporating profile to two segments, one with a vapor flow zone that we can model separately, and one with a liquid flow zone that we can actually model with the Richards equation. And here we get to what we call a critical pressure head that disrupts the hydraulic conductivity. Okay, so the critical pressure head, the question is, how do we quantify that for our model? And this is work of Lehman et al. From 2008 with Shmuel Asulin, and they look at the different textures, and they defined a static pressure head that defined this, this connection. And this was based on the retention curve. But if you base characteristic disconnect on the retention curve, then you discard hydraulic non-equilibrium, because again, you have only one location that disconnects liquid continuity. Later work with pore network modeling and some experimental work of from the 90s showed that the disconnect actually happening at very close to a unit or a minus unit gradient of flow. Okay, so let's look here. Here I plot the water distribution, okay, here on the horizontal versus the height above the water table for liquid continuity. And the dashed line here shows the hydrostatic distribution. The red and the blue line show the Gardner's solution up to infinity and theta R. And the yellow marker shows where the hydraulic disconnect happens when we actually use a unit gradient. And so this defines this dashed evaporative front. And you see, you get different heights and different locations of theta, values of water content, disconnecting the liquid continuity depending on the flow rate. So this is currently what we are proposing to use. And so our concept is that we have some soil properties that define the water distribution, and we can solve for the liquid continuity up to a specific point that is defined by the hydraulic function of the soil. And this location provides us both the water content at this evaporative front and the location of that evaporative front above the water table. Okay, so then we can construct two equations. The liquid flow, we integrate from a water table to that pressure head that we just defined. And above it, we have vapor flow, which we can just, here we use Fickian diffusion of vapor gradients. And we assume that because this process is very slow, we assume that for each profile, we have a steady state. So the liquid flow is equal to the vapor flow. And then we can basically solve this very simple set of equations. Then we can construct the entire evaporation process. Basically, we have the first stage is stage one. We can solve by assuming hydraulic continuity and finding the location when this is disrupted. And then we can go to a second stage where we have both a vapor phase region above the evaporating front and a liquid phase region below it. Okay, just to give an example of how this influences the modeling, and then we'll go to some more validation. So this is just model run. This is using two soils if we assume hydraulic continuity to the surface and the Gardner model. Now we can see that if we introduce a vapor phase, it depends on the soil properties. For example, for the Chofetz sand, the vapor phase almost doesn't change the model results. But for this clay loam, it has a vast influence. So depending on the water content, on the water table depth, here with Gardner's model, we get to basically zero evaporation. But if we introduce a vapor phase region, we keep fairly steady evaporation rate. And we think this is a much more physical approach for the system. Okay, so let's look at the time. Okay, good. The proposed model, now we go and validate it with some data. But before that, we basically looked at this, we assume steady state for each evaporating profile, and then we collate these steady state to get a continuous function. The first thing we wanted to do, hey, let's look at the full differential equations, solve them numerically, and compare those to our simplifying assumption. And basically, we see a very good agreement. I'm just showing the visual results. But essentially, our simplified approach gives errors of less than 1% in the cumulative evaporation. The next thing is taking data, and as I promised, this is data from Shmuel and co-authors from 2013. They did a lysimeter experiment, and they took high resolution, spatial resolution sampling of water content. And what of the upper 20 centimeters. And this plot shows a zoom in to this area, and this plot is from their experimental paper showing the same 12 centimeters that I'm showing here. So what we see is that the model that we propose predicts liquid water flow up to this point, then an evaporating front, and vapor diffusion from this location up to the surface. Okay, the blue line is Gardner's model, and you see it would predict high thetas or high water contents above the evaporated front, and this dashed line is the hydrostatic line. So the data supports our model. So with the data here showing up to this point, you will have water contents above the residual water contents, and approximately above this location, you would have water contents that are below residual and in between residual and approaching zero. And from the images of the experimental work, we can see that this kind of evaporating front changes during the day. And we only simulated here one of these scenarios representing the average day conditions. It is important to say that there is no inverse in this solution. So there's no data fitting, only taking the soil properties, the atmospheric condition, the water table depth, and predicting the evaporation rate and the water distribution. Okay, so the next thing we wanted to look at is actually an evaporating dynamic profile, starting from saturated condition, going to stage 1 and continuing to stage 2. And so if we look, we look at a period of about 40 days. This is experimental work from Hamra sandy loam. And this is the model. And there's not much to say about apart from again saying that there's no fitting of the data. It's only using atmospheric condition and soil properties. Because we only had this cumulative evaporation from this experiment. But going to a next experiment, a different soil, a coarse sand now under a low evaporating condition of atmospheric demand, we have additional data of a measurement of the water table depth, or where the metric potential equals 0. And then we can compare both the cumulative evaporation and the water table depth data and modeling prediction. And we can also look at what the model predicts with the water content distribution. And here, I also show where the model predicts the evaporated front to be. So between here, where metric potential equals 0 until the evaporated front would be a water distribution up to theta R. Okay, so this is shown by this scale, and above it, an evaporated front with vapor diffusion from this location to the soil surface. Okay, a little bit more about the model, about soil hydraulic properties and different initial conditions. As for now, we only looked at starting in this scenario, we looked at where we start from saturated conditions as an initial condition. Okay, so here is a plot of the upper plots show the first stage of 1 millimeter per day, and the bottom plots show 1 centimeter per day stage 1 evaporation. The plots on the left show the cumulative evaporation, and the plots on the right show the depth from the surface. Of the dashed lines are the evaporated front, and the continuous lines are the ones that represent where the metric potential is equal to 0. And we have 3 soils here: Hamra in red, fine sand in black, and coarse sand in green. And we can see that even under the same demand for stage 1, each one of these disconnects at a different point. The other thing we can see is that really immediately when we initiate this, when we initiate evaporation, the location of H equals 0, which begins at the surface, drops first quickly and then goes gradually. And this initial drop is related to the air entry value of the soil. And again, this shows us different behaviors and dynamics of the soil as we would predict by evaporation. The other thing, just to demonstrate the ability to use different initial conditions, if we take the same data as I showed from the Hamra before, we take this model and we take and we state the atmospheric demand, but now instead of saturated initial conditions where we had surface at 0.48%, we now, 48%, we now start with surface wetness conditions of wet, and we see this is almost the same as saturated and dry. And I took dry condition, which can still sustain stage 1, but we see it disconnecting at an earlier stage because of the disconnect of hydraulic conductivity. Okay, so going to talk a little bit about what I'm thinking of doing next. So we essentially built a framework that can model the hydraulic disconnection. One thing that is seen with layered system is that if you have a coarse layer over a fine layer, then you would have the disconnection from the atmosphere. But if you have a coarse layer below a fine layer, then you would actually get hydraulic disconnection within the coarse layer. And so this is something we want to test with our approach. And this will surely show us the effect of rate and hydraulic disconnection. The other thing that we didn't see yet, but we want to work on, there's a lot of issues with what's called enhanced diffusion. So we model diffusion under continuous linear vapor concentration gradients. But in the case, if we have some liquid water coming into the soil when it's dry, this can cause shortening of vapor paths, or even some liquid that forms continuity even in an area that is basically non-continuous, but is above what we call the hydraulic continuity area. And this can cause what's called, or what's known as enhanced diffusion. And this, of course, here, this image also shows that this will depend on the shape of the grains. And for this, what I want to do is insert the coupled heat and water processes. This is images from which we saw before. edge changing of the day, we get some areas of this liquid coming to maybe areas of here, maybe condensating here. And this can happen, you know, if we look at the temperature change in the soil. We can basically, here we show an image of 4 a.m. and 8 a.m. And we can see the profile temperature changing as a function of depth. So this would be, this can cause condensation and evaporation of liquid in the profile and can maybe lead to enhanced diffusion. Okay, so thanks for your attention. I think I left a lot of time for questions. Ofer?
Yes, please, if you have questions, go ahead.
I have a question.
We are trying to ask a question.
Nope.
Hi. Are you aware of any effects or work that's done to understand the relations between these separate layers and the microbiome? Because you basically show that there is one layer which is more desiccated and then the other layer is wetter. So that should separate the microbiome between these two layers. Are you aware of any work of that kind?
No, I'm not. Just keep in mind that in terms of the amount of water needed for microbes there, saying that we go to a vapor zone doesn't mean that there's not enough vapor or vapor concentration, vapor amounts for microbes to be there. I mean, this area in terms of microbes should, I'm not sure you should see a much difference unless you're very close to a very dry surface, because very good aeration in this area. If you go a little bit below the surface, you would get very moderated soil temperature. And I think enough water, of course, depending on the dryness of the condition, right? If you have a very low water table and you have a very dry environment, then you would have a thick dry layer. And then at the very top, you may have very dry conditions that will limit microbes.
What I meant is basically show that there is one layer which may be susceptible to periodic desiccation, real desiccation, and then other layer which probably will be less prone to this periodic desiccation. And that, I think, should separate the population there. The area which is the upper layer should be inhabited by organisms that enable to withstand this periodic desiccation.
Yeah, but again, in terms of temperature and in terms of available water, I don't see this happening.
I think this affect the movement between the communities. So yes, you when it is dry, you can live, but you cannot move and seek for other hotspots of nutrients. So this will affect the mobility of the different part of the community. And in the dry area, there will be limited, they will not exchange They will not go for hotspots of nutrient. They will not exchange DNA and things like that.
I have a question. Thank you for the interesting lecture. And as of the steady state model you present, if it's a 1D model and you constrain it that the liquid flux due to the matrix tension until in the deep part of the unsaturated zone is equal to the diffusive vapor flux above this front. So this is imposed that in the clay, as you showed it, in the clay or fine texture soil, no, it doesn't matter wherever the water table is, you all will have about a constant flux, a vapor until the surface. Now, isn't this too heavy an assumption that this is the major process that happens? And as you showed, you had where you compare the sandy and the 31 here, I think 30, number 30, or 31, yeah. Here, as you see, the liquid vapor, it doesn't care where you say no matter what, if there's the water table can be 20 meters or 200 meters below surface, the vapor flux will be 1 millimeter per year. So, do you think this
Yeah, well, the main thing here is that this is a log scale, and it's a very large log scale. So this is actually what you see here as a straight line. It's a decreasing rate. The main thing is that here the rate is decreased by the vapor. So when here we went with only liquid, once we get to a lower water table, it really, because of the hydraulic function of this soil, it really goes to lower unphysical rates. But here, no, it says, well, if you're too low, no worries. Vapor diffusion will keep it. And this is just an artifact of the scale. It actually, when you look at a zoom-in scale or a linear scale, this just decreases and decreases dramatically, because when we go to deep water tables, the vapor diffusion zone is huge, and so it does limit. But the main point here is that we wanted to outline this difference between these two approaches and how the vapor diffusion actually provides the path to keep evaporation at, let's say, physical, more realistic rates.
Okay. I wasn't aware of the scale that it's -5 each slot. Okay.
More questions, anyone? Now's the time. Okay, if not, then Tamir, thank you very much.
Okay, thanks a lot.
And thanks everyone else who participated.